SwayamPrabha. Digital India. Educated India.
Hello, welcome everyone. Today we will continue on discussing the metathesis reaction. You have seen ring closing metathesis or RCM. In the last class, we have discussed the last example about the 2-in and 1-ine reaction. So, di-9 reaction. The molecule was having 2-in and 1-ine. Initially, the organometallic intermediate was formed at one of the terminal in. Subsequently, that organometallic intermediate containing part reacted with alkyne because that was the more favored ring formation, which will give rise to 5-membered ring, and those 5-membered ring containing metallocycle then reacted with another in to give a fused 5 and 6-membered ring formation. Today, we will discuss some more example of this ring closing metathesis reaction. First of all, one problem always we have to encounter, and that is the geometry, controlling the geometry of the olefin that is generated during these RCM reactions. Well, of course, the olefin can be cis or trans in nature. Let us look at the first example, one example where 2-terminal olefin is undergoing ring closing metathesis to give a huge something like 19-membered ring formation, and in the process what we see that the product is a mixture of cis and trans. So, let us look at one of those examples. When we are looking at this molecule, this is reported by Shuji, we have seen that the 2 olefin are there on the terminal position, they are interlinked by an ester. Now, in presence of a tungsten catalyst, okay, we have the ring closing metathesis in progress. Overall, if we react this to terminal olefin, we will get a 19-membered ring, 7 from this alkyl part, 8 from this alkyl part. Overall, it becomes a 19-membered ring. However, in these cases it gives a mixture of cis and trans product. Now, there are not too many ways to control these cis and trans product formation. One of the way to control the cis and trans product formation or the controlling the geometry could be reacting with an alkyne instead of an olefin. So, these reactions are going to be alkylidene chemistry, where an alkyne instead of an olefin is reacted with the organometallic intermediate. During the process, of course, if the 2 alkynes terminal position, 2 alkynes are reacted, those alkyne will give rise to the newer alkyne where there is no problem of any geometry. Now, that linear that alkyne, the final product alkyne, if one is reducing with a suitable reducing agent, then one can control the geometry of the olefin. Let us try to look at these alkylidene ring closing metathesis reactions and how to control the geometry in those cases. The example which we will discuss first is by Aloy Fuchsner. Okay. So, this is a terminal alkyne, not in truest sense, but there is an alkyl group on both the side of the alkyne. Now, what Fürstner has done, now this compound he has synthesized and he has taken Schrock catalyst, that is the carbene, tungsten catalyst with carbene along with tertiary butoxide 3. This is the tungsten reagent that he has taken, and this you can call as Schrock alkylidine. Under this condition, what one can synthesize is, of course, these two alkyne will clip and will give rise to this interesting compound. In a moment we will see. This is 5 of them and that. So, this is the one which is going to be the final product, where 2 alkyne is reacted with an alkylidine and it is undergoing a ring closing metathesis reaction. Now, that is a very interesting product, because 2 alkyne is giving rise to another alkyne, which is now really a huge membered ring in the process. Overall, if one is trying to react between 2 olefin, namely terminal olefin or even internal olefin, during the process controlling the geometry is extremely difficult. One way to solve this, or rather not directly solving it, would be taking alkyne. 2 alkynes will undergo this metathesis reaction in presence of an alkylidine species, that is an organometallic species. The one we have seen is from Schrock, where tungsten alkylidine is reacted with the 2 alkyne substrate within one molecule to give rise to the internal alkyne. In the process, the huge ring that is formed can now be reduced with, for example, Lindlar's catalyst, which is a palladium hydrogen catalyst. Now, in presence of that, now you can control the geometry of the olefin, which is generated from alkyne, in a way you want. Overall, if you look at this product, then we will see this alkyne to olefin conversion and the product formation leading to a world famous perfume, and which is very cool way to synthesize this perfume. Okay. Let us look at that molecule again that we have synthesized. So, this is the compound we have synthesized by using this Schrock alkylidine species, and it has been reported by Fürstner. From here on, we can react it with palladium hydrogen, that is the Lindlar's catalyst. Overall, we will be able to get this civetone. This is the oldest perfume that is known. This is the ingredient of oldest perfume, and it is usually used in under extreme dilute condition. So, this is used very dilute, and it can be synthesized by a chemist quite easily. Now, of course, this perfume industry is widely dependent on this ring closing metathesis reaction. I am sure all of us have used perfume at one point of our life, or almost some people may be using regularly. Other perfume that is quite famous is Muscone. of course, there is a natural source, but you do not want to kill a lot of deer to get the muscone, right. This is of course illegal at this point, and therefore, scientist has relied on synthesis of this perfume, and a lot of these perfumes are nowadays synthesized chemically rather than utilizing the natural resources, because those natural resources are scarce, and you do not want to go or push any animal into extinction by doing extraction of this perfume. So, the muscone, for example, can also be synthesized by a similar pathway that we have synthesized or we have shown for civetone, which is the world's oldest perfume known, and muscone is the one which is nowadays used quite widely. Let us look at the structure of the muscone. This is again a ketone, this is a very cool molecule, and this can be synthesized. So, this olefin can be generated, this olefin can be generated by utilizing the similar procedure. So, overall what we have seen that any huge ring can be generated in the process of doing the ring closing metathesis reaction. Technically, any terminal olefin or olefin at any position, two of those can be put together to generate yet another olefin. Of course, same is true for alkyne. One can put together two different alkyne together to form a new alkyne in the process. But let us look at that chemistry of the alkyne leading tungsten species, which has been studied in details, and even there exists a crystal structure which gives the idea about the intermediate that is involved during the process. Let us look at the mechanism. So, mechanism for these alkyl leading species. So, we are taking the tungsten alkylidine reacting with another alkyne. Overall, it is a 2+2 reaction to give you tungsten intermediate. The most interesting part of this is now characterized by X-ray. Now, what in X-ray it is found that all the bonds over here are equivalent, all bond lengths are equal. Overall, you can give a canonical structure for this in the double bond then shifted based on the fact that all the bond lengths are equal. You can see that you can say that this is a this is a resonance structure between these two species, right. So, these are resonance structure, and subsequently if one is undergoing retro 2+2, we can get the tungsten with another alkyl leading moiety, and this has to be really interesting at this point, because we overall we get this new tungsten alkylidine intermediate. So, we started with a shock catalyst, that is tungsten alkylidine, we reacted with a alkyne. Overall, it is a 4-membered transition state or 4-membered intermediate that we find. This is crystallographically characterized, which clearly suggests that between the two structures there is a resonance, and therefore, all the bond lengths are found to be equal, and this gives rise to a clear mechanistic idea how this might will be happening during those ring closing metathesis reaction. Next topic that we would like to discuss is carbonyl olefination. Now, all of us are familiar with carbonyl olefination in our undergraduate studies or graduate studies. These olefin, converting these carbonyl olefination reactions are mostly known in terms of this Wittig reaction, right. Of course, there is no organometallic intermediate involved, although Wittig reaction is quite popular. It is every reason to be popular, but a number of cases Wittig reaction does not work. Then if you want those Wittig like product, what is the alternative? Well, you have this metathesis reaction to rely on to get those Wittig like product. Now, let us look at the pros and cons of this metathesis reaction to synthesize the carbonyl olefinated product. Carbonyl olefination is the next topic that we would like to discuss. Carbonyl olefination, also alkylidins chemistry, these are stoichiometric reaction. Of course, that is true also for the Wittig reaction. The chemistry we would discuss today is with the Strock carbene. This is the Strock carbene. This you can draw in a different fashion as we have discussed. Strock carbene is nucleophilic at the carbon center. This is similar to what you know about the Wittig reagent. This is your Wittig reagent, and this is a equivalent thing for a Strock carbene reaction. Now, overall what you do in the Wittig reaction is this triphenyl phosphine and this alkylidin equivalent, you react with, let us say, R2 aldehyde overall to give a intermediate where you have HR1 and let us say HR2O minus. From there you get R1 and R2 H along with triphenyl phosphine oxide. Now, if you look at this chemistry of the Wittig reaction, of course, you are able to generate a olefin from an ketone. Now, similarly, if you are using this carbene chemistry, those of Strock metathesis reaction, metathesis reagent, Strock catalyst, if you are using and reacting with olefin, you can get exactly similar product as you get in Wittig reaction. Let us look at one of the example where Strock carbene is used for the Wittig reagents. Now, this is done by Strock in early 80s, 1976 rather, 1976 by Strock. He reacted it, his Strock catalyst, which became famous later on, reacted with a olefin to give an intermediate which looks like just your Wittig reagent, Wittig intermediate. Now, if you do that, overall you have a 2+2 and a retro 2+2 to give you the tantalum oxide, much similar to your phosphine oxide, and the product that you get in the process has the tert-butyl part, because the tert-butyl you started with the reagent, now tert-butyl ended up with the product. Now, this reagent, if similarly if you want to react with a lot of other reagent, you can react with a number of ketone to get the corresponding product. As you know, Wittig reagent really does not work with ester. That is one of the limitation of the Wittig reaction. But if you are interested in this Strock carbene, for example, you can react with ester, of course aldehyde, ketone, ester at will to get the product that you desired. From the ketone to corresponding olefin product you can get in acceptable yields. The same thing we cannot tell about the Wittig reagent, because Wittig reagent fails with the ester. Let us look at one of those example where ester is reacted with the Strock carbene to give you the newer olefin. First of all, let us look at one of the ketone example. I think that we have discussed. During this process, overall we get this T-butyl containing ketone in 80% yield. Okay, that is great. Interestingly, as I was telling, that ester also react to give you the corresponding olefin in 60% yield. Now, Wittig reaction of course does not work with the ester, because ester is less nucleophilic in nature. Now, another case where Wittig reaction does not work is the, let us say, DMF. If you want to do Wittig reaction on DMF, can you do that? Of course, you cannot, because it is that aldehyde center is less nucleophilic in nature. You cannot get a Wittig reaction with DMF. Now, DMF or even ester, any ester you cannot do, and this is where this Strock carbene or the metathesis type of reaction becomes much more interesting and can give the product, and it is used industrially in lot of cases where Wittig reaction is failing, and these reactions are now used as an extremely dependable alternative for the Wittig reaction. Let us look at one more example with DMF. Now, DMF is the one, this one. So, these are even less or lower nucleophile compared to aldehyde. From there on you can get using this your Strock carbene, you can use the reagent. Now, that is fine when a lot of limitations is there in Wittig reagent. You can utilize this carbene chemistry to get the desired product, namely ester and amide, which never really participates in the Wittig reaction. But there is a problem in these cases, because as you see in all the product, the final compound, if you look at carefully, there is a tert-butyl unit invariably. Whatever you want to do, that comes in. So, that got to be the limitation of such reactions, where you cannot have any other alkyl group at the olefin partner. Now, if you are okay with the tert-butyl group, if your target molecule requires to be tert-butyl, that is fine, but if you do not want that, this is when the Tebbe's reagent becomes much more useful, and it is actually found to be quite versatile, even more versatile than Strock's this carbene chemistry. So, let us look at the Tebbe's reagent and let us try to see what it can do. Of course, these reagents are alternative to the Wittig reaction. When Wittig reaction has no way to deal with the product formation, Wittig reaction fails completely, then when Strock carbene comes into picture, and of course, your Tebbe's reagent comes into picture. Strock and Tebbe's reagent of course works very well for aldehyde ketone and every other things, but one may not want to use them when Wittig reagent is working, but when Wittig reagent is not working, this is the only way to move forward with the ketone to olefin product formation. So, Tebbe's reagent, as you know, Tebbe's reagent is a titanium species. This is cyclopentadienyl titanium species, which is ready to give you the active catalyst from there on. This is done in 1978. So, these are methylinates. The reactive species are the one where this is dicyclopentadiene titanium methylinates is forming, and this is better in scope compared to even the Strock one, better than Strock in scope. So, by using the Tebbe's reagent, one can use, of course, one can react with aldehyde, ester, ketone, amide and whatever other reagent which is incompatible with the Wittig reagent can now be incorporated quite efficiently. Let us look at one of those examples by which this Tebbe's reagent can be of great use. First of all, let us look at the ester. Of course, as we have discussed, these are not compatible with Wittig. Amide, ketones, all can be aldehyde, everything can be reacted with Tebbe's reagent. This can be reacted with Tebbe's reagent. The one example that we will discuss specifically is the one where you have enolizable proton, for example, this ketone. Now, if you are reacting this reagent, this ketone with Wittig reagent, you get very little product, because there is a enolizable proton which is not compatible with the Wittig reagent. Now, so therefore, if you take PH3P double bond CH2, this is very little product. You get enolization as the side product or side reaction. Now, these are Tebbe's reagent, can be used over here very beautifully, because these are less Bronsted basic and therefore, lesser ability to accept proton. So, less enolization you can expect. So, less Bronsted acid, Tebbe's reagent is less Bronsted acid, and therefore, it is not promoting the enolization that very effectively, and overall we can then get quite a good reaction with these Tebbe's reagent. So, these ketone which are enolizable, they usually give you the side reaction as the enolization as the side reaction, which is what the problem with the Wittig reaction is. Now, using Tebbe's reagent, you can get or convert these ketone into corresponding olefin without any problem. Once again, then what we have discussed in this class, that Wittig reagent is a reliable reagent for converting aldehyde and ketone to corresponding olefin. However, in a number of cases, Wittig reagent does not work, and this is where Strock carbene can be extremely beneficial. And the problem with the Strock carbene is it leaves a terbutyl, or the carbene terminal is getting incorporated into the product. Often we may not want that into our product, although it works decent with ester, it works well with even the amide. This is when the Strock carbene cannot be utilized for some of the substrate. Tebbe's reagent, I would say, is most versatile and can be used widely. Of course, it can react with aldehyde, ketone, ester, amide. These works beautifully. So, it is a very good reagent with respect to the Wittig reagent. Now, whenever Wittig reagent fails, I would like you to think about the Tebbe's reagent. Even for those ketone which are having enolizable proton, one can react those reagents to get the corresponding ketone to olefin product formation. All right. So, in the class so far, we have discussed about mainly the Strock carbene and its reactivity. We have seen how the Strock carbene has developed and some of the reactivity pattern of the Strock carbene. In the next class, we will get back to Fischer carbene and their reactivity pattern. Till then, keep studying. We will see you in the next class.